Hello everyone, I'm Zhiyuan from UCSD. Today I'm going to present our work, Mira, a program behavior-guided file memory system. This work is done in collaboration with Zijian and Professor Yiying Zhang. Let's get started. Nowadays, low and imbalanced memory utilization has become a major problem in data centers. The emerging file memory technologies utilize slower memory tiers beyond the main memory, and even beyond server boundaries to solve this problem. They place memory on slower tiers, including remote DRAM, non-volatile memory, and use RDMA or CXL to connect them back to compute server to increase resource utilization. However, one major problem still exists in file memory system world. That is, how to port applications onto them. That requires enabling program to place and access data stored in file memory. Existing file memory systems could be categorized into two major classes. One focusing on application layer, and another focusing on system layer. The first, application-centric approach, create new file memory programming models. Programmers need to rewrite their programs utilizing the new file memory APIs. In this process, programmers can explicitly express and optimize for file memory accesses. However, this requires much programmer's effort to do the rewriting and cannot adapt to different dynamic behaviors, including runtime size change and execution hot point change. This could lead to overhead on both human and runtime side. In contrast, transparent file memory systems transparently swaps local memory to file memory at runtime or operating system layer. This requires no program changes at all. However, it is unaware of what application is doing and have no adoption to different applications. This means that it always keeps a single set of caching and accessing policy, which could lead to inefficient memory operations at runtime, including fetching or writing unused data to remote, and with no or even wrong prefetching. With both approaches have major issues, can we find a way to build a file memory system that is both transparent and efficient? We propose to do this from a new layer in between and use a behavior-guided way to build our file memory system. This means that we start from understanding the program behavior and then generate both application and system side from it. We use a co-design of program analysis, compiling, and profiling to achieve the behavior-guided goal. Our solution is Mira, a behavior-guided file memory system. Mira starts with unmodified applications. First, Mira uses program analysis to capture the static behavior, including the access sequence, data locality, and many other things. Then, Mira uses the profiling collected during the execution to capture dynamic behaviors, including the object size and execution overheads. After getting both behaviors, Mira uses a compiler to integrate all behaviors and transparently generate the file memory program, including transforming the program to access file memory and configure optimal file memory runtime system. Finally, Mira runs the process in profile-guided loops to iteratively adapt to new discovered and changing program behaviors. With all this, Mira successfully capture and utilize a full view of program behavior. Compared to state-of-the-art file memory systems, Mira outperforms them by 43 to 70%. Now, let's see what's the major challenge in Mira and how do we solve it. The major challenge and really novel part in Mira is how we can generate efficient file memory program based on program behaviors. This is not a simple job even for experienced programmers and manually ported programs, as file memory accessing have an unavoidable non-trivial overhead. For example, if you want to access some data located in local memory, it will take tens of nanoseconds. However, if you want to directly access some data located in far memory, it can take you several microseconds to finish. Existing far memory systems introduce far memory cache and different far memory accessing policies, trying to let more access hit only in the local cache to mitigate this overhead. And these two policies became the key to far memory performance. One problem of existing systems is they are using a single global cache with unified accessing policy for a single program. The major problem of one unified cache is objects with different behaviors coexist in a single program. In this example code snippet, we have two variables. One is array, which is a vector, and another is table, which is a hash table. The array is sequentially accessed in a loop. Every element in the array is accessed exactly once and requires no caching. However, in contrast, the table is accessed near randomly and have no notable spatial locality and predictable temporal locality. This too shows distinct behaviors, and both need to be captured in the generated programs. At the policy level, these different patterns require totally different accessing and caching configurations. For accessing policy, the array requires batched access to increase the throughput, while the table should be accessed best at the per-element granularity. Similarly, for caching policy, the array could utilize a quite simple stretch-plan memory, but the table we better use the least recent used base cache to capture the hottest objects to be cached. A single, unified cache is impossible to optimize for all these distinct behaviors at the same time. Leveraging our knowledge of the behaviors, Mira's solution to this is to separate the local cache into smaller sections based on program behaviors. We observed that in far memory systems, all global caches are software-managed DRAM cache. As Mira can already identify different behaviors, we could fully utilize this feature and split the whole cache into a set of smaller sections, which each section customized just for one single type of behavior. With this isolation, we can customize the property of each section, including cache size, structure, prefetch and eviction policy, just to exactly fit the behavior's needs. After separating cache sections, we could achieve efficient application porting to far memory in two steps. First, we configure each separate cache section according to its behavior. And second, based on the behavior and the section configuration, we generate optimal access for each occurrence of far memory access to the object in the cache section. Let's see how Mira implements these two steps in more detail. First, Mira takes an iterative approach to refine the configuration with behavior learned from each iteration. We will start the first iteration with a modified program. Mira, at this time, without knowing any runtime information, just choose to place all the data objects in a generic swap section. In such a case, Mira acts like a transparent swap system. The key difference is Mira closely monitors all memory allocations and runtime accesses. The understanded dynamic behavior is used in later executions. In the second iteration, Mira profile finds optimization targets, which is object and corresponding functions with high execution overhead. In this example, we identify this sequentially accessed array and corresponding function. After seeing the targets and observe that its behavior is different from existing sections, Mira tries to create a separate section and place the object into it. By looking at its source code, analyzing its accessing patterns, as well considering its runtime behavior, including size and access frequencies, Mira selects a set of optimal cache configuration for it. For this sequential accessed array, it uses a large line size plus a sequential-based prefetch. This optimizes performance. After finish the configuration, Mira generate program and run with new configuration. In later iterations, Mira continues on the optimization loop, finding new targets to update and do the new configuration based on the new behavior. We will do this until no optimization target is found or maximum number of iterations is reached. In our evaluated applications, this process converges within 4 iterations. With the cache section configured, Mira then trying to find the optimal way to generate file memory access code. Accessing file memory is different from accessing local memory, which could incur a high overhead for accessing alone. For example, when you want to access something in the local, you just need to convert the access into a load and store instruction. However, when you want to access data stored in the remote, that is, dereferencing a pointer that points to a remote data, you need to go through several steps. First, you need to acquire remote address correctly. And second, you need to look up if the data is already in the local cache. And if not, you need to fetch the data back from the remote. And finally, you need to acquire the local address for the cache data. After all this, you could access your data. One naive way of porting to remote memory is doing all those steps for every single access occurred in the program. However, could we actually do better here? Our idea is to generate file memory access automatically and adaptively according to the access logic, leveraging our static analysis. Mira could utilize the program residency info from the static analysis and cache configuration when possible to try to avoid or optimize those remote memory dereferencing steps at every remote access. Let's see how this works with 2 examples. First, Mira could eliminate unnecessary point dereferencing. However, when we move to access the second field in the data structure, do we need to do everything again? Not really. The static analysis tells us the 2 accesses is back-to-back, and the cache line will not be evicted as the access set of the second field. That means that we can jump over all these steps and convert the second access to a raw memory access. Mira could do this across control flow and function boundaries, which could be hard even for a programmer to identify. Next, with static analysis, we could optimize the steps by prefetching and evictions. In our loop accessing example, as we know that all the elements in the array will be accessed in order in the future. If we do everything in a naive way, we will spend a lot of time waiting on fetching data between 2 accesses. However, leveraging our analysis information, we could plan for future access earlier. We could potentially optimize the remote fetching step by making it happen earlier and interleaving the fetching and accessing. Use prefetching to fetch them earlier successfully reduce overall latency. We have a lot of similar adaptive optimizations, including access batching, selective transmission, RDMA transport selection, and function offloading. Please check our paper for more details. We implement Mira compilers on top of MLIR compiler infrastructure. As 2 new dialects, Remotable dialect and RMRef dialect. We implement our configurable runtime library on top of user space RDMA and Linux user FortFD for the swap sections. We compare Mira with state-of-the-art swapping system, FastSwap, and state-of-the-art file memory programming model AFM. For C++ data frame application, we show relative performance against running everything on the local as y-axis and different percentage of local memory available as x-axis. Mira achieves near optimal performance, as shown in the figure. Compared to AFM, without having adaptive generation, AFM incurs a high runtime overhead even if it's given a lot of local memory that is able to hold the whole work inside. Compared to fast swap, Mira section separation greatly reduces interference between different data object accesses and makes it perform better when local memory is low. Also, Mira analysis prefetch is more precise and have less wrong prefetching. We run Mira on several typical data center workloads. On different types of applications, we still outperforms those state-of-the-art systems. On data frame, Mira reduces the access interference and could benefit from function offloading. On GPT inference, a machine learning inference job which have fixed access sequence, Mira could perfectly capture the access pattern and schedule all the prefetching and accesses at static time. Finally, we evaluated Mira on graph application MCF, which features more random and indirect access pattern. Mira still outperforms existing systems, leveraging its cache section isolation and prefetching hints. As a conclusion, Mira is the first attempt to build a behavior-guided file memory system. It achieves application-aware and transparent at the same time. Our main takeaway is application semantic is becoming more and more important with systems becoming more complex and tiered like file memory systems. We need program semantics to be captured and utilized at system layers to be able to actually build performance-optimized systems. Mira demonstrates that a co-designing of compiling, profiling, and analysis could be a good way to achieve this goal, and it could be potentially utilized by many other systems. Thank you, and I'm happy to take questions.
Please, go ahead.
Who am I asking to? Okay. Hi, hey, thanks. Good talk. I had two questions for you. The first question is, apart from sequential prefetching, have you considered any other type of prefetching? And the second question is, how does your work compare to the ASPLOS 2020 paper on classifying memory access patterns for prefetching? Even though that was for caches, I think that would be highly applicable, or it's highly related, because they also use prefetch injection in code. So I was curious to know how you compare to that work.
Okay, thanks for the question. So for the first question about the pattern types, so basically we are not trying to classify different prefetching types. We are trying to, for example, for the sequential prefetching, we are trying to use a technology in compiler called scalar evaluation to trying to figure out what will be accessed statically in the future. So we do not rely on classifying those prefetching types at runtime, but instead we are trying to figure out what will be accessed in the future at static time as much as possible. So this, as we explain in the paper, this will result in more accurate prefetching and can cover more taps. For example, besides the prefetching, in the MCF application we are showing, it is a graph accessing, but we can still follow the pointers, use the already fetched pointer value to trying to prefetch the value is 0.2. And that's kind of indirect prefetching. And in our example, we're also including the structured types, prefetching types. But our system's ability is not limited to these types. Basically, if we can figure out what we'll be accessing in the future in the static time, we can do the prefetch. And for the second question, sorry, I'm not very familiar with that paper. They're trying to figure out and inject the prefetch hints. So if you can introduce more detail how it is implemented, we can do a quick analysis on what's the difference between us and that paper. Thank you.
Thanks. Yeah.
Hi, Kyle Hale, Illinois Tech. Really great work. Thanks for the talk. I have a question about the loop analysis that you showed. So it was a very simple loop, I think, with like an incremental counter. So I wonder if you're using like a simple induction variable analysis there, or is it something more complex, like polyhedral analysis?
Thanks for your question. So as we mentioned, we're mostly reusing the LLVM's scalar evaluation there. So it's not purely symbolic. So basically, we still need to find some. We are trying to predict the value of the induction variable there. So yeah, that's the current implementation.
Cool. Thank you.
And I'll ask a question too. So how do the benefits provided by Mira change as the application input changes? Do you see, did you evaluate that or?
Yeah, so thanks for a good question. So yes, our system do adapt to input value changes. That goes to like what's our target applications. So we have a relative huge assumption here. That is, we're targeting data center applications, and data center applications behavior changes slowly. That means that even the input is changed, the behavior of the program, like the hot point, the performance, which part leads to the most remote execution still remains the same. And this is proved by a lot of like previous profile-guided profiling works. And Mira adapts to different inputs by adapting to this kind of similar behavior. One example could be like if you are targeting a key value store system, even that they can have different key value stores, they can have different size of the key value store, but as long as that they have the same behavior, that is, this key value store is, for example, have some hot site and should be cached in the local, Mira can identify it and optimize for it, and do not need to redo this for different inputs. And our experiments actually shows this. All of our evaluation in the paper are training on a different site and evaluate on another site. So this shows that we have ability to adapt to different input sites with the similar behavior. And if you are interested in more detail, you can check our paper. Thank you.
All right, let's thank our speaker again.